So my position for this talk, and generally my position really, is that we need neuro-symbolic approaches. So the neural approaches are what you've heard of in the news, ChatGPT and similar. And my position is that we need to really combine such neural approaches with mathematically rigorous, symbolic, traditional AI approaches to actually make this successful in the future. So I'll be talking about some of the projects that I've worked on over the past 10 plus years. So this is one of the projects. It's called a graphical solution configurator. And the idea of this was to be able to make it possible for manufacturing SMEs to enter, to reduce the barrier to entry so that they can actually start creating digital solutions by themselves with no programming knowledge needed, without the need to recruit systems integrators and coders, okay? So the idea is to give them this design platform, as you see a couple of screenshots there, so that you can essentially put together building blocks that correspond to actual solutions. You've got, for example, a Raspberry Pi, a computer on the left-hand side. You can connect a database to it. You can connect a sensor to it. You can connect a different type of camera to it. And you design it in this manner, and you essentially click a button saying generate code. And that generates code, and it also generates a bunch of instructions that tells you how to purchase those pieces of hardware, connect them together, and run the code on top of it. Because without the hardware, there's nowhere for the code to run, right? So it gives you instructions as well as it generates code on your behalf. Now, the innovation in this particular system is that not just that it's claiming to be user-friendly using this building block like programming language that you see on the left-hand side, but it's also somewhat mathematically rigorous. So there's a mathematical kind of description of the framework that disallows certain activities, disallows certain connections, do not connect that particular camera to that particular computer because they're incompatible, for example. It also, this mathematically rigorous framework also lets you take into account SME requirements. So these are some of the real requirements we've had when deploying solutions at manufacturing SME facilities. So for example, avoid recording voice. I know that you're using a computer. Surely there's a microphone in there. Can you make sure that no voice is never recorded on our factory floor? Can you make sure that you stick to Windows 10 or later? And can you make sure, for example, that if you're logging data, can you make sure that it's logged locally and not remotely in some sort of a cloud server due to privacy reasons, right? So the idea of this mathematically rigorous kind of underlying framework is that you can guarantee these requirements are met, as opposed to using kind of a neural approach that doesn't necessarily give you those guarantees. So I want to take you through an example where we have actually deployed kind of a solution at a manufacturing SME. You can see the building blocks corresponding to the solution on the right-hand side. We put this together manually. The point is that we were able to create a building block-based solution relatively quickly, within 45 minutes to an hour, at an actual SME, and give them a working solution, right? But you can imagine that going forward, you make it even more user-friendly. Building blocks are user-friendly. SMEs were able to understand these building blocks, but you can make it even more user-friendly and interface that with, for example, a large language model such as ChatGPT. And you start talking to this system, which puts the solution together, still using building blocks, not using arbitrary code, still using building blocks. And let's say I've asked the system to do the stuff that I've shown you on the left-hand side here. I've given it a bunch of instructions. It's put together the corresponding building blocks that you can see on the right-hand side. And I'm going to give it a couple more instructions that you can see flashing on the left-hand side there. Can you please monitor the heater on indicator? Using this building blocks approach, but I'm giving these instructions to ChatGPT, which is in turn controlling the building block configurator, right? You can see that it's recognized that is the component that I'm talking about. It's created the necessary building blocks for it. It's drawing rectangles, and I'm also asked it to generate a visualization dashboard for me. so that I can actually visualize digitally what's going on in the factory. The factory is full of analog panels, which we're not supposed to touch. We can install a camera that looks at it and digitalizes it, as you see in a second there. So it's a camera facing a bunch of panels, it digitalizes it, and it shows me the result on my laptop, right? So that is the digital solution. And the advantage of using ChatGPT is, of course, that it is more user-friendly than the building block-based approach. But we are not using ChatGPT in the way that it's used at the moment. We are not using it to generate arbitrary Python code, because firstly, Python code is not necessarily understandable by manufacturing SMEs, right? They don't necessarily have an expert who can code. And secondly, Python code, we don't really know what that code is going to do, because LLMs are known to hallucinate. But LLMs are still useful here because they're not generating arbitrary Python code, but they're generating building blocks. And our building block framework makes sure that those building blocks don't do anything that goes against requirements given to us by the SMEs, or does crazy things that you're not supposed to do, right? Now, I won't go through all of these deployments, but there's quite a few deployments of this solution at manufacturing facilities. You can check out the website on the bottom left there. Going forward, we'd like to deploy more of these solutions using the configurator that I showed you earlier. Only some of these are currently deployed by that automated approach that I talked about. And we'd also like to interface LLMs in the manner that I described, right? So that's the first case study that I wanted to discuss. The second one, there's quite a number of demonstrators that we were given access to at the University of Nottingham. All of them essentially had the same system running. I'll only focus on the demonstrator at the bottom there. So the demonstrator at the top is essentially a customized pharmaceuticals production plant. It's a proof of concept platform that lets you create custom pharmaceuticals for customers based on their needs. On the right-hand side, we see an aircraft rib manufacturing plant that lets you create ribs for aircraft wings, I believe. And on the bottom, you see a vehicle hinge assembly platform that is an actual platform that is used to assemble vehicle hinges for BMW or whatever that vehicle was. And the idea is that we made this system completely controlled by an agentic AI system, right? So a symbolic AI system that controls the whole platform, and we use computer vision to double check that the assembly went as expected. So it's a neuro-symbolic kind of interaction there, and the system can also be formally verified. So we can make sure that the system does what it's supposed to do. And let's look at an example of how this works. So initially, the customer or the person chooses the product that they want to manufacture, and then you ask the system, can you do this? The system at the moment says, I cannot manufacture this because there's something missing. So you go ahead and you realize that there's no camera that is needed for the final test to see if the product was assembled properly. So you attach that camera and you ask the system the same question. Can you now do this? And the system now says, yes, this is manufacturable. I've got all the resources and everything is in place so that I can give you the product that you want. If that's the case, you can go ahead and load the raw materials into the fixture there and let the agent system run the show, right? So you trigger the agent system starts controlling the shuttle. It starts controlling the first robot, which does a part of the assembly of that hinge that you requested, the particular hinge that you requested. It does the assembly, it puts it back on the conveyor belt. It hands it over to the second robot. The agent system figures out what that second robot should do, what tools to use from the tool changing rack, and so on. And the second robot then hands it back over to the third station, which you will see in a second. So you can see the hinge there. It's doing some activities on the hinge to finish it off. And then you hand it over to the vision system that double checks that the assembly went as planned. So this is using machine vision. It could use deep learning. It could use anything that looks at a picture and checks that the assembly went according to plan. And if it didn't go according to plan, it could potentially go back in that same conveyor belt, get disassembled and reassembled. Now, I'm not going to go through the details here, but essentially we had an underlying mathematical framework which was used to model each of the individual kind of robots, to model the conveyor belt, to model the camera system, and so on, in the form of graphs, let's say. And we had a technique that put all these graphs together to create what we call a topology, as you see in the bottom left here. So topology is essentially the layout of all the resources in the manufacturing plant, and it represents all the possible things that this production facility can do. So later on, when you ask the system, can you manufacture this hinge, or can you make me an iPhone? It can check that request against this massive graph that tells you all the possible things that the facility can do. So this enables, for example, bidding for products online, like you have in eBay. You could imagine multiple manufacturing facilities distributed across the UK, and you ask them, can you do this? And they can automatically check whether they can. And this is correct by construction, in the sense that it is provably correct. So if it says it can do it, it can actually do it. It's not hallucinating. It can actually do it. And if it can do it, it generates what we call a controller that essentially talks about how to orchestrate the various robots and the conveyor belt and the testing system and the cameras and so on to be able to do the actual manufacturing of that product that you requested. Now, this is a mathematically rigorous description that you see here in the middle there, but it's not necessarily understandable or explainable to your factory manager. So which is why we've made it explainable by translating that into what we call P2MML, which is an ISA standard, which is more of a standard. And if you say that that's not understandable either, which makes sense, that's where strategically we can kind of link up LLMs, for example, to explain that to your grandmother, right? So it becomes that next level of user friendliness. But the point is that stuff in the center here is provably correct, and we can make sure that the system is safe. We can guarantee it. We can create. We can start certifying these systems, and we can start explaining this to the relevant stakeholders, right? So I'll go through my third case study, which is a construction setting here. So we've got an autonomous rover that goes around kind of assessing a construction facility to find various problems. For example, people have left their hard hats. There's some rubble in the way that could be hazardous, and so on. This system is also verifiable, so it's got kind of a verifiable system running the show at the bottom. So the robot is controlled by a mathematically rigorous framework, but at the top, there's an agentic system that is running the show to some extent. And that agentic system, although it was a symbolic system, you could imagine in the current day, in the current era, you can actually replace that old agentic system with ChatGPT or some ChatGPT-based agent. The point is that even if a neural network is controlling this robot, we know that the underlying framework here is not going to let that neural network do whatever it wants. It's going to keep the robot always in a safe state, regardless of what you're telling it to do. So let's go straight into an example. So we've got that robot out in the field. It's got 3 layers of sensors. It's got cameras right at the top, the panoramic camera right at the top. It's got some cameras in the middle there, the red cameras, and it's got a laser scanner at the bottom. There's an agent system controlling the whole thing, as you can see on the left here. And there's a verification engine at the bottom. So that verification engine is what makes sure that the robot is always in a safe state, regardless of what you ask it to do. It will always double check and make sure that it's safe to do it, right? For example, keep enough distance from construction site workers, and make sure that you don't navigate using both your cameras and the LiDAR scanner and the laser scanner at the same time, because the engineers have said that this system was not built to do that. as opposed to current autonomous cars might rely on that, but this system was not built to be able to navigate using laser scanners as well as cameras. So you can see that it's going on. It is taking pictures of the surroundings using the panoramic camera. It recognized that somebody has forgotten that this is not the most useful example, right? But there are other examples where it's recognizing hazards. But in this case, somebody has forgotten their safety jacket, or whatever you call that, and an operator is notified who comes and takes that jacket, and the robot makes sure that it keeps a distance from the operator. It doesn't move while the operator is there, and it navigates safely because it is controlled by a verifiable, mathematically rigorous bottom layer. Okay. So just to demonstrate what I mean by that, imagine this ChatGPT or some other agent system that is controlling this, and it sends the wrong request. Like I said before, you cannot navigate using both cameras and the laser scanner at the same time. So I'm going to make it do that, try and make it do that. Ask it to navigate using cameras at the beginning. Then I'm going to immediately ask it to also navigate using the laser scanners. And we are just checking that the verification engine at the bottom catches that to be a dangerous potential state and rejects that request back to the agent system and says, look, so you can see that it's going to catch that request and say it's in red, which means that it's not allowed. And it sends an error message back to whoever asked it to do it. So in this case, it was an agent system. In the future, it could be ChatGPT, a ChatGPT based agent, for example. And it says, you're not allowed to do that. And you could imagine the neural network learning from this. So it provides kind of a safe haven for a neural network to learn in actual construction size, because the robot is not going to do anything undesirable. So it's okay for the neural network to do mistakes as long as those mistakes are caught. Now, my second last slide is the current project that I'm working on. I won't go into the details of this. There's a website at the top, and all the websites are repeated on the last slide as well. So this is in the context of, again, construction. It's to go around on UK highways to recognize, using neural networks, as you can see in the bottom here, issues on the road network, on assets, various types of assets. And in this case, it's recognizing cracks and classifying those cracks using neural networks. Once it's recognized, it hands over that information to a symbolic system that figures out what to do about it. What material should I use? Should it be bitumen? How much should I inject? At what flow rate, and what is the optimal trajectory that I should follow while I inject that material onto the surface of the road. So those are some of the use case studies that I've worked on in the past. And going forward, I'd really like to see a much cleverer and much deeper integration of the neural and the symbolic components in a way that, for example, lets you translate from a large language model into a mathematical representation as you abstract it higher and higher. And then what that allows you to do is to be able to explain to a user what this large language model is doing. And there are many people working on such interesting research problems. So just to summarize, I think LLMs are great. That is why AI is getting revamped and it's making impact because of LLMs and neural networks. But I think that's one nice piece of the puzzle. And I think another useful piece of the puzzle is to really go back to the AI that came in the 1950s, which is symbolic AI, and to fuse them in a manner that is useful for construction and manufacturing and other sectors, because it guarantees reliability and explainability as well.